Welcome to a new session. Today we are going to study one application of Gauss's law. We know by Gauss's law we can easily obtain the electric field for some simple symmetric charge configurations. Here in this video we are going to find electric field due to a uniformly charged infinite plane sheet. For that, we are going to consider an infinite plane sheet of charge density sigma. So here we are considering a small part of it, and the surface charge density of this infinite plane sheet is sigma. We assume the charge is uniformly distributed, therefore sigma is uniform charge density. We know if sigma is positive, that is greater than 0, then direction of electric field is outwards, and if sigma is less than 0, that is negative, then direction of electric field is inwards. For this case, we are going to consider this infinite plane sheet is positively charged, so that the direction of electric field is outward and with a uniform charge density sigma. To find the electric field due to this uniformly charged infinite plane sheet, consider a cylindrical Gaussian surface with a radius r and length 2l like this, so that this length is L and this length is L. So the length of this cylindrical Gaussian surface is 2L, and area of this cross section at n points we can take it as A. We also know the electric field due to this plane sheet are normal to the surface and it is outward, as we consider the charge is positive. We know according to Gauss's law, electric flux through a closed surface is closed integral E dot ds is equal to 1 by epsilon 0 times the charge enclosed in that surface. So now we are going to apply Gauss's law here to find the electric field due to this uniformly charged infinite plane sheet. For that, we need to find the value for left hand side of this equation and then equate it with the right hand side. So we are going to calculate the electric flux through this closed surface. We know the direction of electric field is normal to this plane sheet. That means the direction of electric field is parallel to the curved cylindrical surface. So here the direction of electric field is parallel to the curved cylindrical surface, therefore electric flux through this curved cylindrical surface is 0. This is because the direction of electric field is perpendicular to the direction of ds, that is normal to the ds element here on the curved cylindrical surface. That makes theta is 90 and E dot ds as 0. Therefore, the electric flux through the curved cylindrical surface of this cylindrical Gaussian surface is 0. Now we can see the direction of electric field is parallel to the normal of the small element at a cross-sectional area. Therefore, we can see it contributes to the electric flux. We know the electric flux is equal to E dot ds, and it becomes E ds here because theta is 0. That is, the direction of outward normal to the small element ds on the cross-sectional area and the direction of electric field are same. Therefore, E dot ds becomes E ds. And to find the total electric flux, we need to integrate it. If we integrate it, we know it will get E into integral of ds. For one cross-sectional area, integral of ds is area of this cross-section, and we take area of this cross-section as A. But we know there are two cross-sectional areas here through which electric field passes. Therefore, integral ds is 2 into A. Therefore, this integral becomes 2EA. So, the electric flux through the cross-sectional area is 2EA, where A is the cross-sectional area of the cylindrical Gaussian surface. Since the electric flux through the curved surface, that is a curved cylindrical surface, is 0, the electric flux through the closed surface, that is closed integral E dot ds, is only due to the cross-sectional area, that is 2EA. So we got the left hand side for this Gauss's law. Now we know, according to Gauss's law, this is equal to 1 by epsilon 0 times q, where q is the charge inside that Gaussian surface. We know the charge density of this plane sheet is sigma, and the area of this plane sheet inside the Gaussian surface is A. Therefore, the total charge inside the Gaussian surface is Q is equal to sigma A. We can substitute here, so this becomes 1 by epsilon 0 times sigma A. So we got the equation as 2EA is equal to 1 by epsilon 0 times sigma A. A we can cancel. So we can write the electric field, that is the magnitude of electric field, is equal to sigma divided by 2 epsilon 0. So we got the equation for the electric field due to an infinite plane sheet of charge with a uniform charge density sigma. We can represent it vectorially as E is equal to sigma divided by 2 epsilon 0 into n cap, where n cap is the unit vector normal to the plane and going away from it. So from this equation you can easily see if sigma is positive, E is outwards, and if sigma is negative, E is inwards. So here we found the electric field due to a uniformly charged infinite plane sheet. Thank you for watching this video. Keep learning. If you are not yet subscribed to our channel, please subscribe it. Also, please like and share this video.